All right, thank you for the introduction. So it can be tempting to look at sort of this toy model of our solar system here, and you can see the orbital changes, but other than that, you think, well, probably these planets are as they've always been. They were formed sort of in the place that they are and with the structure that they have today, other than, again, the orbital changes. However, this is not the case. We know exoplanets change with time, specifically the ones in our solar system. We know, for example, that planets change through interactions with the disk that formed them, the gas and the debris that's used to form all of their planets. As the planets move through this, they change in their orbital period. They can move closer to the star or further away. And the same sort of thing can happen as planets interact with each other. They can pull on each other gravitationally. They can also interact with nearby stars as they pass by, or in a binary system. The point being that you can change the orbits of the planets this way. And in fact, we think this exact thing happened in our own solar system. And that's what this animation is meant to show. This is the 4 outer planets, Jupiter, Saturn, Neptune, and Uranus, and their orbits very early on when the solar system was young, just a few tens or hundreds of millions of years old, and then a much more dense Kuiper belt, outer comets, than what we have today. And as the planetary system evolves, all of these comets are kicked out through these orbits. And then very, very quickly, all the orbits of the outer planets change. And this gives us the kind of orbits that we have today. Very different than what they started with. And it's not just orbits that are changing, it's also the structures of the planets themselves. We think the young solar system was loaded with debris, the kind of debris you get from the Kuiper belt, but also just dust, material left over from the formation of planets. In addition to that, there were tons of small protoplanets colliding with each other all throughout our history. And in fact, these collisions are often invoked to explain the formation of the moon. A large proto-Earth collides with something about the size of Mars, and the end result is the Earth-Moon system. But these collisions are happening constantly. Probably all the planets in the solar system underwent some sort of collision like this, whether small or large. And the bigger point I'm trying to get across is that planets, as we see them today, they don't change on sort of our lifetime scales, but on longer time scales, they change significantly. Planets evolve. They look very different when they're young. And we want to understand what kinds of processes drive these to understand more about not just the Earth, but also all the thousands of exoplanets we've discovered through various missions like Kepler. What happens with these systems is that you're seeing just a snapshot in time, kind of like what we're seeing in the solar system today. You get just how they are now. And because most of the planets we know today outside the solar system are old, many billions of years old, we know very little about what they were like when they were young. And it may turn out that these processes, things that happen when they're young, things like planetary collisions or changes in orbits of gas giants, are very important. Many people believe that the orbital changes between the gas giants I showed you in the simulation earlier is an essential fact for the formation of life on Earth, because it helped protect us from all those Kuiper belt objects that could have collided with the Earth later on and impeded the evolution of life on our own planet. So these processes might be very important. And we can do geology here on Earth and in our own solar system to learn about the history of our planet, because certain rocks and minerals, they last a very long time. So you can learn a lot about the history of our solar system, but we can't do that with exoplanets. So instead, we have to use another technique. So one idea is to find some young planetary system just after it's formed, and you could just, say, stare at it for billions of years. So this doesn't work for one really important reason, which is that the timescales of interest, something like 1 billion years, are really way too large compared to your average PhD thesis. I think even a particularly slow PhD thesis would not really get at this. So there are other ways through simulations. There are limitations, but the method that I prefer to use, and this is a trick a lot of astronomers use, we use this to study galaxies, planets, all sorts of things, is to look at planets at a range of ages. So you imagine creating some diagram like this, where you have some parameter of interest, like how thick the atmosphere is, or how the orbits of the planets are, or just how big or massive the planet is. Anything you're interested in that you think changes, and you look at young planets, and you look at middle-aged planets, and you look at older planets, kind of like the solar system. And let's just take atmosphere as an example. Let's pretend that you looked at a set of young planets and you found that when we compared them to the older planets, the ones that all the current missions find, you saw something like this. And this would tell you immediately that atmospheres grow with time, that they start out small, and through some sort of process, outgassing from the planet interior or collection from asteroids or comets, the atmospheres are growing. Whereas if you saw something like this, you might say, well, planets are born with very thick atmospheres, and they lose them over time. And you might say, well, if this happens for the Earth-like planets, that means we're in trouble if a planet can't hold its atmosphere, if most exoplanets can't hold its atmosphere. And then it would raise the question, why did our planet hold its atmosphere, or get the atmosphere that it has today? And then you could imagine something like this, where you say, well, the atmospheres basically don't change. We can just assume that the snapshot we get from Kepler is the true reality of what these atmospheres look like at all time. And I just use atmospheres as an example, right? You can pick any parameter you want. And you might say, great, so problem solved. This is how we study the history of planetary systems. Except it turns out this is extremely difficult to do. And the main reason is that it's almost impossible to measure the age of a star. And we assume that the planet's age is the same as the star's age. That's a pretty safe assumption, but it doesn't help very much if you don't know what the star's age. So there's a few caveats to that. There are some ways. One of them is this method called gyrochronology. It's simply that stars spin faster when they're young, and they slow down over time. So if you can measure how quickly they're spinning, what their rotation period is, by staring at their light curves. So basically what's happening is spots are moving in and out of your field of view, and so the light curve varies at the rotation period. And if you measure something that's rotating slowly, you know it's old, and quickly it's young. And this is great for a very small set of stars, basically stars just like the sun. But it does not work on most stars. And this is generally true. This is true of almost all techniques we use to measure the ages of stars. It simply doesn't work on the vast majority of stars, and the errors are just too big. We measure things like the star is older than a few gigayears or less than a few gigayears. This is just not a precise method, not enough to make a plot like the one I was showing you before. So the method that I use, and has become sort of more popular recently, is to look at stars where we already know the ages independently, specifically stellar clusters. And the ones I look at are Praesepe, Hyades, Pleiades, and Upper Scorpius. And probably many of you have heard of some of these. These are sort of the nearest young clusters to the sun. So some of them are quite famous. You can see Pleiades in the night sky. Hyades is a little too diffuse to see, but Pleiades is, of course, quite famous. And the advantage of these regions is that all the stars form from the same molecular cloud at the same time. So they all have the same age. So any method you use to measure the ages of these stars applies to all of them. So it doesn't matter that whatever technique you use only applies to 10% of the stars. You know all of their ages immediately. And in fact, usually methods like gyrochronology are calibrated on these clusters. It's usually the other way around because their ages are known with such precision. And these span the ages of interest. There's very young systems right after the planets have formed. There's something older compared to these young ones, but still relatively young. And there's sort of something in between. And these are the timescales we think that planets change on. So we think we're really getting at the truth of things here. And I won't go into all the details of all the little things we found in these various clusters. I do want to highlight one system in particular, in part because it had a press release, so it has like a pretty diagram, which is K233. It's always nice. You do NASA press releases, you work with Nature, and they make all the artwork for you. So it makes these presentations a lot easier. K233 is particularly interesting because this one's in Upper Scorpius. It's only 10 or 11 million years old. And it's also on an extremely tight orbit. Here it is compared to the solar system. You can see it's far inward of Mercury. The period is only about 5 days. And you remember before I was talking about different ways in which exoplanets migrate. I mentioned disk migration. This is planets interacting with the young stellar disk, or planets interacting with other planets or stars in the same system. So it turns out this mechanism, the second mechanism, is what we think happened in the solar system, but it's very slow. It takes hundreds of millions of years. Whereas this method is very fast. It takes less than 10 million years. And because this planet is only about 10 or 11 million years old, we know instantly it must have migrated through this mechanism. And this just highlights the power of young exoplanets to answer questions about how planets evolve. We know instantly what happened with this system and how planets evolve generally just by finding it. All you had to do was discover it and its orbital period, and you get this answer. But thinking more about the big picture questions we can answer, not just about how planets change, but also about the history of our own planet. So look forward to sort of technology that's coming in the near future, and think about sort of big questions, the big questions we want to answer. Now, there's a huge amount of resources going into finding an oxygen planet, an O2 planet. And the reason for this is that O2 is considered the key biomarker. It's difficult to maintain oxygen in an atmosphere without photosynthesis. It's not impossible, but it's very difficult. And so if we find an oxygen atmosphere around another planet, there's a very high likelihood that there is photosynthesis going on. There's plant life on that planet. And so this is a very worthy and important goal. This is one of the main goals of the James Webb Space Mission, to find this. However, I think a similarly important question is the history of these kinds of systems and their atmospheres. What kind of conditions give rise to an oxygen-rich planet, to a habitable planet, to sort of the Earth 2.0 is the buzzword. Now, we know that a young Earth had an atmosphere very different than the one it has today. It probably had a hydrogen-helium atmosphere, something it picked up from the disk from which it formed. But Earth doesn't have enough mass, so it loses this atmosphere extremely quickly. A massive planet like Jupiter can hold on to it, but not Earth. And instead, the modern atmosphere is a product of outgassing and then of photosynthesis and a number of geological and biological processes that happen over hundreds of millions of years. And so while some groups are looking for this modern Earth, this O2 planet, what I think is similarly important is finding these, finding young analogs of Earth to see what their atmospheres look like. Is what we think about an early Earth right? Or is what we think about an adolescent Earth right? Does it turn out that these planets look very different than we think ours did? And so you can imagine a scenario where it turns out that the evolution of our own Earth was not quite what we thought it was. And then we look at a range of planets that are otherwise very similar to Earth. They looked very different when they were young. So this isn't just answering questions about exoplanet evolution. It's really answering questions about our own history as well. And that's a good place to stop and take questions.
Thank you, Exo Man. We have some time for questions. Oh, let's go with this gentleman over here.
Yeah, the method you described with gyrochronology seems very similar to a Kepler works with the planetary transition in terms of reducing the light of the star. How can you tell whether the star's light is being reduced by a sunspot or a planet?
Yeah, so the question was, the gyrochronology method I talked about, you're seeing star spots move across the star, and it looks quite similar to the method we use to detect the planets, which is a transit. And how do we tell the difference between those two? Because both of them cause a dip in the light curve. So it's a really good question, and actually it's a significant problem for exoplanet searches like Kepler. The basic answer is that we take advantage of the fact that the timescales are very different. So a typical star will rotate on a 10-day period, say, or maybe 50 days or 100 days. And that's a very slow process, whereas a planet will move across a star in a matter of hours. And there's, of course, the median case where the stars are very young, and they're rotating very fast, and so they might move across in hours, which is the stars I study, and so it's a huge problem there. And so there we have to take advantage of more advanced techniques like looking at the transit in different colors or taking advantage of the shape differences, things like that. So, yeah.
Right in front.
So the question was that the solar system, from appearances, seems pretty stable. Are there any things that are changing more rapidly? And to my knowledge, no. The solar system is extremely stable. Not much is changing. Things are changing on long time scales. You know, the Earth-Moon orbit is changing on long enough time scales. But I'll defer slightly to a solar system expert. I'm not aware of anything in the solar system that's changing on extremely rapid, like less than million-year time scales or less. So, other than things on the Earth.
Right there.
Yeah, so the question is, I talked about finding, sort of studying the history of Earth-like planets, and how would we do that if, with all of Kepler, we actually haven't found a perfect Earth analog? So in some sense, you're taking a statistical step. What you're doing is you're looking at a number of systems that are sort of similar to Earth and looking for patterns. So while we haven't found a perfect Earth analog, we haven't found a one Earth radius planet at 1 AU around, the 5700 Kelvin star. We found a lot of planets that are very close to that. We found planets around slightly cooler stars that are slightly inward and get the same amount of flux from their host star. And we found one slightly outward of that. And whether or not you consider those Earth-like is a question of how tightly you want to cut your bin. The reality is these studies will happen at the same time. People will be looking for oxygen atmospheres, and so we're going to know when we find those what constitutes an Earth-like planet. It may turn out that planets much closer to their star can have oxygen atmospheres, in which case I'm going to look for the young analogs of those, right? So this is all science that's going on at the same time, and you're doing many, many systems and sort of taking statistical averages over it. So it doesn't matter that you don't have a perfect analog.
In the back? Yep.
And how big is an AU in terms of mile over kilometers?
So I believe, this is like pulling back to graduate student quals. 93 million miles, I think, is the number for an AU.
Lady down in front.
How do you tell what type of atmosphere a planet has so far away?
So the question is, how do you tell what kind of atmosphere a planet has? That's a really great question. And if I had tons of time here, this would be that would have been that was in the original version of the talk, and of course it was 30 minutes then. So we use this method called transmission spectroscopy. It's not the only method. That's the method I use. And what you're actually doing is, man, I wish I had kept the slide in there. But what you're actually doing is when you see a transit, a planet passes in front of its star, it blocks some of the light. And if you imagine some thin atmosphere on that, some of the light passes through the atmosphere, but some doesn't. And at different colors, at different wavelengths, how much light passes through changes. And it's just like the Earth's atmosphere. It blocks certain wavelengths, which is why we can't do astronomy at certain wavelengths, basically. And we know what wavelengths certain atoms and molecules block at. So you look at those wavelengths, and then you're like, okay, that molecule is present in this atmosphere. And it's the same sort of thing when you're looking for oxygen. We know what wavelengths oxygen blocks at. So we look at the transit in that wavelength, and if it's deeper, the transit is larger than it should be compared to other wavelengths, we know that atom is present. And it's actually way, way, way harder than that because this measurement is like, 0.001% or something difference. It's incredibly small.
But it's really cool. Okay. I think that's it. We're going to go on to our next speaker. Let's thank Mann again.